Hi everyone, thanks for coming to the talk today. I'm pleased to introduce Xiao, who is from the computer science department here, where she's an assistant professor. Her research focuses on database theory and its applications to practical data systems, including parallel and distributed query processing, dynamic query processing, data privacy, and algebraic techniques for query optimization. Last year was a very good year for Xiao, with her work recognized at PODS with a Distinguished Paper Award, the SIGMOD Best Paper Award Honorable Mention Award, and the ICDT Best Paper Award, all in 2024. So please tell us about query processing.
Okay. Thank you for the invitation and introduction. So I'm Xiao Hu from the School of Computer Science. Today I'm very happy to be here and share with you some recent theoretical advancement in computing join aggregate queries. I know the term join aggregate may sound very specific to databases, but this is a very general class of queries that can capture many commonly studied problems as special cases. For example, the subgraph pattern matching problem, the constraint satisfiability problem, and the matrix multiplication problem. And I hope that this talk can be a starting point to connecting the database research and the theoretical research, since we are interested in so many common problems, but just talk in different language. So this is the outline of my talk today. The first half of my talk will focus on an overview of this research area. So I will define the join aggregate queries and give you some examples of the join aggregate queries. Then we will review the classical result in the literature and then share our recent new results for computing join aggregate queries. Due to the time limit, I won't cover much technical details, but all those new results and the proofs can be found in these 3 papers. So the first one is fast matrix multiplication for query processing. Second one is output optimal algorithm for acyclic join aggregate queries. And the last one is fast matrix multiplication mixed submodular with. So in the second half of the talk, I will use 2 examples to illustrate the high-level idea behind our new algorithm. So the first example is an output optimal algorithm for computing the chain matrix multiplication problem. And the second example is how to use fast matrix multiplication to speed up computing the star matrix multiplication problem. At the last, I will discuss a few interesting open questions in this area. Okay, the first interesting application of join aggregate queries in graph analytics. Okay, suppose we are given such a graph, you may ask a few interesting questions. For example, is there a click in the graph? How many triangles in the graph? If this is a weighted graph, what is the minimum weight triangle in the graph, and what is the minimum length key path in the graph? So all those queries can be captured by the join aggregate queries. As an example, let me use listing the triangle query as an example to see how can we express this query in database language. So in the relational data model, data is stored into tables or relations. So every column here is an attribute, and every row corresponds to a data record or a tuple. So to encode the information of the graph, we use the table to store the edge information. So these 2 attributes encodes the 2 endpoints of the edges. So every row here corresponds to an edge, directed edge in the graph. Okay, and to find the triangles, we need 3 identical copies of the edge relation, but just rename the attributes into A, B, BC, and CA. Okay, then I introduce the join operator in database. So the join operator is defined on 2 tables, which is to find all pairs of tuples from these 2 relations that share the same value on their common attribute. Okay, if we use E1, table E1 join table E2 join table E3, we can find all the triangles in the graph. For example, the tuple Alice Bob will join with the tuple Bob David on their common attribute B, and Bob David will join with David Alice on the common attribute C, and again Alice Bob will join David Alice on the attribute A. So this corresponds to a triangle join result Alice Bob David. Okay, so So the join problem is essentially a graph pattern matching problem, or generalized hypergraph pattern matching problem. Okay. There are some other examples in the graph analytics that can be expressed by the join aggregate queries. For example, the shortest path, the maximum reliability problem, the calculability problems. Okay. Another interesting example I want to share is the matrix multiplication problem. Here we are given 2 Boolean input matrix and 1 output matrix. So in database language, we will encode each matrix as a table. So we use 2 attributes. The first attribute to encode the row index of the matrix, and the second attribute to encode the column index of the matrix. So every tuple here corresponds to the coordinates of a non-zero entry in the matrix. Okay. So under this representation, we can say that this output matrix is exactly the join result of these 2 tables, and then we just drop the join attribute B. Okay, so if you look at this entry in the output matrix, so we can say it's the computation of this row and this column, and if you trace this database instance, so it's the join result of this 2112, 2332, and these 2 join results share the same value on A and C. We just drop the middle column B and remove duplicate. So we will get this query result 2 and 2 in the third table. Okay, any question? Okay, great. Okay, after these 2 examples, I will formally define the join aggregate query. So the first question is, what is a natural join query? So here for simplicity, we are given a bunch of tables, R1, R2 to Rk, and each of them is defined on a subset of attributes. So the join operator will combine the tuples from those relations, so each from one relation, such that they share the same value on their common attribute. If we put this in a more formal way, so the result of this query is all the tuples defined on the domain of the attributes, such that for each relation, its projection onto each relation corresponds to a valid input tuple in a corresponding relation. Okay.
In the previous matrix multiplication example, do you need the matrices to have non-negative entries for it to work? Drop the middle column?
No, here I just use the Boolean matrix to, you can have the integer matrix. That's fine. So that's another semi-ring. We will talk soon in the slides. Okay. Yeah. So just use the join operators. We can already express a lot of queries in the graph analytics. For example, listing triangles and listing landscape, path or chains, and listing keyword stars or listing length for cycles. So you just do the join operator on top of those edge relations by just renaming the attributes in the relation of the tables. Okay. Okay, before we define the join aggregate query, we need another notion of commutative semi-rings. Okay, the commutative semi-ring consists of 5 elements. So the first one is the domain of semi-ring elements, and the other 2 is the commutative operators, and we also need 2 another identity elements. Okay, there are several properties to be required for this commutative semi-ring. The first one is that this domain D and this addition and 0 forms a commutative monoid with this identity element 0. And also this D and this multiplication operator and this 1 forms a commutative monoid. And also the multiplication operator distributes over this addition operator. And for the multiplication of any element with 0 still gives us 0. Okay. And if we require the commutative semi-ring to be a ring, we need some additional constraint, which is that the domain D and the addition operator and the 0 also is also a group. Okay, so which requires that for every element in this domain, the additive inverse its additive inverse is also a valid element in this domain. So this condition is required if we want to apply like fast matrix multiplication techniques, because those algorithms relies on the addition inverse operations. Now we are ready to define the join aggregate queries. So this is essentially to compute aggregation on top of the join results. So we already see this underlying multi-way, the natural join query, and now we further specify the attributes into Y and Y bar. So Y bar is the set of attributes that will be aggregated, and Y is the set of attributes that will appear in the final answers. We have seen that if all the attributes are the output attributes, this is a full join. For example, if we want to list the triangles, so all the attributes appear in the final answers. But if you look at the matrix multiplication query, the middle join attribute will be aggregated. So only the head and the tail attribute are the output attribute. So in the join aggregate query, each tuple in the database is annotated with a semi-ring element. And the join operator will multiply the annotations of the tuples participating in this join result. So if you look at the annotation of T is a join result, so you just look at the input tuples in a specific, say this is projection of T on E1, which is the tuple in R1, this is tuple in R2, this is tuple in RK, and they join together to produce T, and we just apply the multiplication on top of their annotations. So the query answers of a join aggregate query is essentially like we first compute all the join results as well as their annotations. Then we partition those join results based on their output attributes into groups. So within each group, we compute the addition of the annotations of those join results. Now each group has one output value, output tuple defined over the output attributes, and one annotation. So those pairs are the query answers for this join aggregate query. Okay, let me get to the question. So you can see this is an integer matrix multiplication. So each tuple in the database now is associated with annotation, which is the value in the corresponding entry here. So you can see that the join operator, the annotation of a join result will be the product of these two annotations, which are the tuples join, producing this join result. And when we're computing the annotation of a query answers, this is 2 and 2, we just find all the join results sharing the same value, 2 and 2, and add the annotations. So we will get this value. So you can see the correspondence between the matrix multiplication computation and this join aggregate query. So the expressiveness of the join aggregate queries comes from the different cumulative semi-rings, the choice of aggregation attributes, and also the join condition. We can say that if we just use like the Boolean semi-ring, and this join aggregate query can capture the conjunctive queries, and also the integer sum product semi-ring to capture the integer matrix multiplication, and there are some other examples. I'm also happy to learn if you catch other applications of join aggregate queries in your research area. I know this is a very powerful class of queries, and I want to emphasize that some of our new results applies for general cumulative semi-ring, so defined over an arbitrary. So this result can be applied if it satisfies some general conditions. So we studied the problem of how to compute the join aggregate queries efficiently in the conventional RAM model. And we focused on the data complexity of this problem and assumed the query complexity, for example, the number of attributes and number of relations as a constant, and only use data-dependent quantities such as the input size and output size as complexity measurement. So for the graph analytical queries, the input size is the number of edges in the graph, and the output size can vary from a single value if you ask a Boolean query or a counting query to a polynomially large number in terms of the input size if you ask to list all the triangles in the graph. And for the matrix multiplication problem, the input size and output size corresponds to the number of non-zero entries in the input and output matrix. So we study those problems in a sparse setting. Okay. And in the literature, one of the most celebratory results for computing joint aggregate query is the Yamakashi algorithm for acyclic queries. Okay, I won't introduce the formal definition of acyclic queries, but just for the graphs, you can interpret it as tree queries. So there's no cycle in their join condition. But for hypergraphs, the definition will be more complicated. The Yamakashi algorithm was proposed in 1981. It's based on a very simple idea, is that we just pick a pair of tables to join and then do aggregation. Okay, if some non-output attributes do not appear later, so we can do the aggregation as early as possible. Then it will materialize their query answers as a bigger table. It will repeat this process until a single table is left, which is also the final query answer. So Yamakashi showed that for acyclic queries, there is a very good ordering of applying this join and aggregation computation. And it shows that for any acyclic join queries, it can be computed in n plus out time. So n is the input size, out is the number of join results. So this is almost the best we can hope for. And this result can be slightly extended to a larger class of queries called the free class queries when aggregation exists. Again, I won't define the free class here, but this is a property to require that the output attributes are well collected by the join condition. Okay. However, for the remaining large class of non-free class query, linear complexity cannot be achieved based on some well-known conjectures. And for example, the matrix multiplication query is acyclic, but not a non-free class. It's not free class, and the people have tried to improve the analysis of the Yamakashi algorithm and show that Yamakashi algorithm requires n times root out for computing the matrix multiplication, and this result is also proved to be output optimal. And this result has been generalized to star queries. So you can see here, star query is a generalization of the matrix query by involving k tables, but all the k tables joining on one attribute B here. Okay, and the exponent on this output size has been increased from 1/2 to 1 minus 1 over k. So k is the number of relations in a query. This result is also output optimal. However, for the large remaining class of acyclic but non-free class query, we only know upper bound, which is n times out. For example, for the chain query, so this is another generalization of the matrix multiplication query. So we have k relations, and their join condition looks like a chain. Okay, and we are interested in the head and the tail attributes, and all the middle join attributes will be aggregated. Okay, so for those queries, we only know this is the upper bound. Okay. So another line of research in the literature has achieved the worst case optimality. I could say this is one of the biggest breakthrough in database theory in the last decade. But worst case optimal algorithms are only designed for join queries, so all the attributes should be outputted. So this line of algorithms can compute any full join query within time of n to the power of rho star. So rho star is the fractional edge covering number of the join query. So this number is to assign weight to the edges such that every vertex is covered by a sum of weight being at least 1. So for the triangle, this number is 1.5. and for K-click is half K, also key cycle is half K, and also for the Loomis weighted join, which is a hypergraph. So there are key attributes here and key relations. Each relation contains all attributes except one, and the fractional edge covering number is K over K minus 1. And this result is also optimal in the sense that the maximum join size has proved to be n to the power of rho star, which is also tight. Okay. So this is for the general join queries. People also trying to combine the Yanakakis algorithm and the worst case optimal algorithm to produce output-sensitive algorithm for cyclic queries. And people use the powerful tool of tree decomposition, which is trying to transform a cyclic queries into an acyclic one by materializing some intermediate join results as one relation. Okay. So by exploring this idea in a more smarter way, people have shown that a general cyclic join aggregate query can be computed in n to the power of some width times out. Okay, so this width is a very complicated definition. So it's the sharp submodular width of general queries. If we are only interested in Boolean queries defined over the Boolean semi-ring, so this width can be improved to submodular width. This general result can recover many classical results. For example, the classic AYZ algorithm in the graph community to detect the K-cycle problem. So this can exactly recover the previous result and can also generate some new result. If we push this idea further, we can transform any non-Frequentless query into Frequentless one if we restrict ourselves to Frequentless tree decomposition. Then after transform any non-Frequentless queries into a Frequentless one, then we can apply the Yanakakis algorithm. So this strategy will give us such a time complexity. And this is a new notion of width for general queries. I want to mention that these two approaches are incomparable, unless we know the exact value of out. Okay? And also for the chain matrix multiplication query, this approach can only give us n square time, which is a very trivial upper bound here. Okay. As a brief summary, so previous result has achieved two flavors of complexity. So worst case complexity, optimal algorithm are good, but the worst case rarely happens in practice, and they are only known for full join queries. Output optimal algorithms are great, but they are much more difficult to design, and output optimal algorithms are only known for Frequentless queries and star queries. So for the large remaining class of queries, we don't know if we can do better than n times out after 40 years. Okay. The first question we want to understand is, what's the lower bound for computing a cyclic join aggregate queries by semi-ring algorithms? So the semi-ring algorithms will work with the semi-ring elements as an abstract type. So they can only copy them from existing semi-ring elements or only generate them by the semi-ring operations. Our first result is to show that, okay, the lower bound for computing general acyclic join aggregate queries is related to the Frequentless fractional hypertree width of the query. We are not the first one to discover this notion of quantity, but we just find that it can be used to calculate the hardness of those queries. I will give a brief idea of this notion. This Frequentless fractional hypertree width, okay, is first we look at all the Frequentless tree decomposition of the query, and for each tree decomposition, we look at each node in this tree, and this is the fractional edge covering number of the node in this tree. Okay, so if you look at this example, this is actually a valid tree decomposition. You can see so each node in this tree decomposition is associated with a subset of attributes, you can see that every relation is covered by at least one node. And more importantly, for every attribute, okay, the nodes containing these attributes is a connected subtree. Okay, so these two properties should be satisfied. Then you can get a tree decomposition. But this is not a free connex one. So let me use another example to show the difference between non-free connex and the free connex. So for the free connex one, we need a connected subtree exactly containing all the output attributes. So in this one, the output attributes are separated across the nodes in the tree. But this one, you can see that there exists one node containing all the output attributes. So this is a free connex tree decomposition for this query. And the width of this query is 4, because if you just look at every node, we need like at least 4 relations to cover each node in this tree. Okay, so this is the, we look over all the possible free connex tree decomposition and find the minimum one. Okay. For example, for the free connex query, this notion equals to 1, and for the star queries with key relations, this is key, and for chain queries with arbitrary relations, this is actually 2. So we can also relate this notion with the previous one in the literature. And interestingly, we find that all those notions collapse just on the acyclic queries. So this also verify our intuition that this is the correct one to characterize the hardness of the queries. Okay, so after understanding the lower bound, our remaining question is for the upper bound. Before we rush into designing new algorithm, we want to have a better understanding of the existing algorithm. So is this n times out upper bound due to the fundamental limitations of the Yamakashi algorithm, or just because we don't have a tight analysis? So in our 2024 paper, we first showed that this algorithm is tight for chain queries. So in the sense that there exist some database instances so on which the Yamakashi algorithm indeed requires n times out time. Now you can see the gap between the existing upper bound and the lower bound we just derived. Okay, so if you can see the out for the chain matrix multiplication is smaller than n squared, so you can see the gap between the upper bound and the lower bound. And we can also generalize this observation for all the acyclic queries. And we show that we identify a class of queries with hierarchical property and show that, okay, the Yamakashi algorithm indeed achieves the optimal complexity on all hierarchical queries. And for the remaining non-hierarchical queries, n times out is a tight analysis of this algorithm. So we can observe a similar gap between the upper bound and the lower bound for all the general acyclic but non-hierarchical queries. So now we are well motivated to designing some new algorithm because the Yamakashi algorithm is not good. And our new result is an output optimal algorithm for general acyclic queries achieving this bound, which is also matched by our previous lower bounds. And we can recover all the previous results, and also we can compute the, for example, the chain matrix multiplication queries within n times root out time. And also, this result can be combined with the tree decomposition method to derive output sensitive algorithm for cyclic queries. Okay, after understanding the semi-ring algorithm, our next question is, can we do better for acyclic join aggregate queries? The answer is yes. We can use fast matrix multiplication to further speed up join project queries, which are defined over the Boolean semi-rings. If we're assuming the exponent omega equals to 2, in the SODA 2024 paper, people have shown that how can we improve the result exponent from 1/2 to 1/3, okay? And in our last 2024 POS paper, we show how can we improve the exponent from 1 minus 1 over k to 2 over 3. And for general cyclic queries, we show this exponent can be improved to 5 over 6. Okay, but we still don't know whether these two results are optimal or not. And for the first result, the authors show some conditional optimality based on some conjectures from the fine-grained complexity. Okay, so next question is beyond the semi-ring algorithm. Yeah, how about this? Can we do better for cyclic join aggregate queries? Yes, yeah, we can use faster matrix multiplication, and in the literature, people have a lot of results for detecting and listing subgraph patterns, for example, triangles, cliques, and cycles. And in a very recent paper, we show how to detect the general hypergraphs using faster matrix multiplication, and we can improve the width from submodular width to omega submodular width, okay, by using faster matrix multiplication. So that's the overview of the new results in this area. I think I will use the remaining time to show you two examples. So in the first examples, we try to use database techniques to improve the chain matrix multiplication. And in the second example, we want to use the fast matrix multiplication to speed up database queries. Okay, the first one is an output optimal algorithm for chain queries. Let's start with some understanding the limitation of the Yalakakis algorithm. So we just, for simplicity, we just look at a length 3 path query. So we only have 3 tables, R1, R2, R3, and we are interested in attributes A1 and A4. Then how to compute this query, I think it's the classical parenthesis algorithm works here. So you just put a parenthesis to the matrix and try to compute the 2 matrices first and then with the remaining matrix. Then the question is, okay, for example, you can put the parenthesis on the first 2, so you compute the join result of these 2 tables and do the aggregation, and then join with the third table and do the aggregation. Or you can put the parentheses on the second and the third matrix. So this will correspond to another database query plan. So you do the join on R2 and R3 aggregation, and then do the join with R1. The question is, which query plan is better? Okay, let me show some instances. Okay, so here we have, this is the database instance just represented as a graph. So every vertex here is a value in the domain of the attribute, and every edge here is a tuple. Okay, so we have this is A1, A2, A3, A4, and those numbers are the domain size. So you can interpret it as the number of distinct values in this attribute. So table R1 is the full Cartesian product. R2 is a one-to-many mapping. This is a many-to-one mapping. Okay. So on this instance, we find that if we join R1, R2 first, it will generate n times out intermediate result. You have to write this down and then do the aggregation, right? But if you join R2, R3 first, you will only generate n intermediate result because there's only one value here. So there will only be at most exactly n intermediate result. So does this mean the second query plan is better than the first one? No. If we just see a symmetric instances, we can say these 2 query plans just have opposite behaviors. So the first query plan only materialize n intermediate result, but the second query plan will intermediate n times out result. Now my question is, given a database instance for this line 3 chain query, can you always find a good query plan? Unfortunately, the answer is no. If we just put these 2 instances together, so both query plans have to materialize n times out intermediate result. So there exists no globally good query plan for the instance. But this bad example precisely points us to the right direction. If we could decompose the database instance into multiple pieces, and it's possible to find a good query plan for each piece of the database. Then we can get a better algorithm. So that's the basic idea behind the hybrid strategy. Okay, before we move to the general chain queries, there are several challenging questions. So first, what to partition? So it's possible to partition the base tables or even partition the intermediate result. And then how to partition depending on which threshold. After we are done with partition, which query plan to pick for each instances. So those are the questions we need to think about. And for simplicity, so far I just assume a constant approximation of the output size is known, and there are many different ways to do that. I will just skip this part. Okay, let's get to the first. Let's get to the third question first. So there are many different plans for computing these chain queries because you can put many different ways to put the parentheses. But actually, we are only interested in two specific query plans. So the first one is that we just do the join and aggregation from the right-hand side to the left-hand side. So we join RK-1 and RK and do the aggregation, and then join with RK-2, so on and so forth, we join with R1. So this is the first query plan we will use. And for the second query plan, yes, symmetrically, we do this opposite. We do the join and aggregation from left-hand side to the right-hand side. Okay. We join R1, R2 first, then with R3 until we join with RK to get the final answers. Okay, then the next question is how and what to partition. I will give you some brief idea here. So we first look at the first join attribute A2 here, and we partition the tuples based on the degree in the table R1. So the degree is the number of tuples it appears in R1. Okay, and we have the threshold tau here. This is a parameter we will determine later. So based on the values in A2, we can partition the tuples in R1 into R heavy, R1 heavy, and R1 light. For the heavy part, okay, we are already done with the partition, and we will choose the query plan for this sub-instance later. But for the light part, we will continue this partition process, but now we will need to change our partition criteria. Now the value A in A3 is heavy if it appears in more than tau tuples in this subquery. So this subquery is we do the join R1 light with R2 and then do the aggregation over A2. Okay, and we will continue this process until we are done with the last join attribute AK. So this partition process will give us k subqueries in total. So in the first k-1 subqueries, at least one attribute is heavy. See this, A2 is heavy, A3 is heavy, A4 is heavy, but for the last subquery, all the join attributes are light. Okay. The remaining question is, okay, which ordering to choose, which query plans to choose? There are only two choices. So for the first case, if there exists some heavy join attributes, we will choose the query plan of from the right-hand side to the left-hand side. The key observation is that since some attributes in the middle is heavy, so it means that it will join with at least the tau distinct values in A1. So the active domain of the last attribute can be bounded. Okay, it's bounded by alpha over tau. So in this query plan, we are always able to carry these last output attributes in this computation. So from right-hand side to left-hand side. So the intermediate result in the computation is always bounded by like n times alpha over tau. And for the remaining case, when all the join attributes are light, means that every value in the middle attributes join with smaller than tau values in A1. So we just do the computation from left-hand side to the right-hand side because the intermediate result can always be bounded by n times tau. Okay. So that's the the basic idea behind this hybrid strategy, we can just choose the value of tau to balance those terms and achieve the final complexity result. But I have to say for the chain queries, because the structure is very simple, we only have 2 query plans to choose. But for the general queries, we need a more complicated recursive partition strategy and more query plans to decide which one to use. Yeah, you can find all those details in the paper. Okay. So that's the first example. The second example, we try to use the faster matrix multiplication to speed up the star queries. Okay, so if we just look at this 3-way star as an example, so we have 3 tables, R1, R2, R3, and all the tables join on the common attribute B. Okay, and we want the A1, A2, A3 to be the output attributes, do the projection. If we look at a hard instance for this query, the hard instance is that there are out to 1/3 distinct values in each output attribute, and in the middle attributes, there are n over out to 1/3 distinct values in B. So every relation here is a full Cartesian product. Okay, it has been shown that no matter which ordering you try to use, we always have to carry the middle join attribute before we join with the last relation, last table. So we have to materialize so many intermediate join results. However, if you apply fast matrix multiplication, for example, we can use the first matrix A1B to encode the first table, and another matrix B, A2, A3 to encode this subquery. Then we can apply fast matrix multiplication to do the computation. And just for this hard instance, we can improve the result from n times out to power 2 over 3 to this term, and if we assume omega equals to 2. If we generalize this idea to arbitrary instances, similar questions arise. First, what and how to partition, and then which query plan to choose. So the second question is much easier. So we only have 2 query plans. Either we apply the Yarlakakis algorithm, or we apply the faster matrix multiplication. But for the first question, we need to be more careful. So the partition criteria is different from the chain queries. So here we look at the degree of each join value in the middle, and we consider a value is heavy if from the second one, third one to the last smallest one, their product is greater than tau and light otherwise. Okay. For this, if the value of B is light, we just apply the Yarlakakis algorithm. If the middle attributes, the values are heavy, we apply the fast matrix multiplication. Okay, for this query, the remaining question is how can we organize the relations into matrix? There are many different ways. You can put R1 as one matrix and R2, the join result R2, R3 into Rk as another matrix, or you can do any partition you want. The idea here is that we will try to balance the first dimension and the third dimension of the matrix so that the computation is minimized. Okay, so we have this assumption that this delta 1 greater than delta 2 greater than delta k. Actually, there are many different orderings here. You can just do the partition. So in each partition, we just assume a uniform ordering between those degrees. And here, we try to put like A1, A3, A5 into, so those numbers as one dimension, and the remaining, the A2, A4, A6 as another dimension of the matrix. Okay. Now I can give you some brief idea about why we do that to minimize the complexity. So first, for the heavy part, we can first show the input size of these 2 matrices because they are very balanced. So the input size can be bounded by n times root out. The observation is that for every B here, the product of their degrees is smaller than out because for every specific value B, it will witness the Cartesian product of those tuples will be the final query answers. So this is always bounded by out. And we just do a very evenly partition on those attributes. So this can be bounded by, just some calculation. You can see that it's bounded by n times root out. Another observation is that the domain of the first dimension and the third dimension of the matrix is always bounded by out over root tau. Okay. Okay. So I will just skip this part here. So the high-level idea is that we will try to minimize the cost of these two parts. So the cost of Yang-Lakakis algorithm is n times tau, and the cost of applying fast matrix multiplication is, okay, this is the first and the third dimension. We just bound the size, and this is the middle dimension. So this is bounded by, this is the cost formula for this operation if we're assuming omega equals to 2. And similarly, we can choose the threshold tau in an appropriate way so that we can minimize the overall cost. So that is the high-level idea behind the algorithm. Okay, so here is a brief summary of the result in this area. So for the matrix multiplication query, if we look at focus on the semi-ring algorithm, is optimally solved. Also for star and also for chain. And very recently, we solved this optimally for acyclic queries. And there are some results for cyclic Boolean queries, but this is only some partial optimality is proved. In general, it's still unknown whether this result is optimal or not. If we jump out of the semi-ring algorithm and using fast matrix multiplication, this is a very new area. You can see the result just have very few results here, and also we don't know their optimality. So yeah, if you are interested about those problems, I'm very happy to talk and collaborate. Okay, I will use the remaining time to mention a few interesting open questions in this area. I think the first next step is to find the combinatorial algorithm for cyclic queries. Beyond combinatorial algorithms, can we apply fast matrix multiplication to the for joint project queries that are defined over commutative rings? There are already some results from both the algorithm community and the database community, but we still need much better understanding of this problem. And beyond the joint project queries, I think we need to think about like the broader application of the fast matrix multiplication. This result technique has been used for approximate counting triangles, cycles, case centering, and dynamic counting. So there are many other opportunities here. We can try to use these techniques to speed up our algorithmic problems. And beyond the theoretical results and the questions we just talked about, I'm also quite interested to see whether we can really apply those algorithms, techniques into the practical database systems. I know it's still a long way, but I think that is the final goal. As a data system person, I really want to see how can we transform the theoretical results into the practice. Okay, so that's all I want to share today. I'm very happy to take questions and also offline discussions. Yeah.
Thank you very much. Does anyone have any questions? Please wait for the mic.
So what is the subroutine of fast matrix multiplication that you consider not combinatorial?
If you have to use the addition inverse.
I'll ask a question. So when at the beginning of your talk, I was excited, and then I realized that a number of problems that I've run into are not quite these join aggregate queries, because you can't decide until that something is a join until you kind of have everything. So it seemed like what you had was this very local requirement that you get, relation 1 and then you connect to relation 2. Does any of this work if you need kind of the whole picture first? If you need to make sure, if you can't decide that they're related until you've seen all, something from all of the relations? That makes sense.
Your question is whether we need to compute all the joint results first before we can.
Yeah, if you have a problem like that, is there anything that you've done that could help with this?
I think okay, if I understand correctly, compute all the joint results first and then do the aggregation on top of the joint result. So that's the baseline solution. Yeah, but we are trying to materialize all the joint results. So this is our target. We want to get some information before we materializing the joint result. Yeah.
Okay.
Yeah.
Other questions? Let's thank Xiao again.
Oh.